Welcome to the latest video in your Design of Experiments course. Well, now what we're getting on to is the alternative way of trying to control standard deviation. And what we're going to take a look at now is finding robustness using the interaction graphs. Now, one of the things to say here about the interaction graph, it can be done using the software. I'm about to do this manually, so I'm going to create an interaction graph out of this very simple experimental data here, but the computer is going to do this for you. But we're going to do it by hand first to give you an insight. We'll finish this video, then we'll show you two exercises where the interaction plot gets plotted using the software, and then how to use that knowledge to turn variables off. That's what we're going to do. In this case, we're going to talk about how to turn A actually off using an interaction. So let's get into this. Let's plot the interaction graph first, then I'll show you how to use it to turn A off. Now then, what we're actually going to do in this little exercise is we're actually going to plot these four results here, but we're going to plot them as two lines. Okay, so you won't see all 4 points plotted as a box. What you'll see is there are two of the data points will be used to draw the first line, two of the data points will be used to draw the second line. So the first thing we have to do before we can draw the interaction plot is work out the summary statistics of the experiment. So here's what we're going to do. We're asking the question, what was the average when we were low for A? So the average when we were low for A is obviously these two results. 14 over 2 is 7. What's the average when A is high? It's obviously these two results, which is these two. 18 over 2. The average is 9. And the delta, the difference between them, is 2. So, and then we'll do the same for the other columns. So what was the average at the low for B? Well, these, of course, are slightly different results now. It's these two results. What's that? 16 over 2. That's the average, 8. What was the average when B was high? These two results, which is also 16 over 2, which is also 8. And the delta, the difference, is 0. Then we come to the interaction. So when the interaction is low, where was that? These middle two numbers, 10. 10 over 2 is 5. When the interaction was high, the two extreme results, these two, 22 over 2, the difference is 11. And then the delta there is 6. So what you can see, look, the biggest effect in this experiment is the two-way interaction AB. Now, in order to understand this, and in order to decide whether I can use it to turn A off, I need to draw a picture of it. So that's what we're going to do now. We're going to draw a picture of this thing. So let's get ourselves a little graph. Let's get some axes for the graph. We're going to plot, what we're going to plot is A across the bottom. So A is going to be across the bottom, at the minus, at the plus. Let's get ourselves a little scale. The highest is 12, 2, 4, 6, 8, 10, 12. So there's 2, 4, 6, 8, Okay, so there's our scale. Okay, so we're going to plot a graph of what A is having an effect on the result. So what is A doing to our system? But we're going to plot two graphs. The first graph is what effect will A have on the system if B is set negatively. So if B is set negatively, where's those two results? B was set negatively at runs 1 and runs 3. So they're the first two results we're going to plot. When A was negative and B was negative, we hit 10. Let's plot that. Now B remains negative, but A goes positive, and we got a result of 6. Let's draw a line through those two. And I'm going to label that the B minus 1 line. Now what we're going to do, of course, is we're going to switch B from the negative to the positive. And we'll draw the same line, but this time B will be held positively. So let's do that. What do we get? When A was negative and B was positive, we hit 4. When A went positive and B was positive, what did we hit? We hit 12. Join those two together. Now that is known as an interaction plot. Now the key point about an interaction plot, when does it show us an interaction? It shows us an interaction when these two lines converge. So they don't have to cross, but they're not parallel. And of course, the more that they kind of turn into one another, or indeed turn away from one another, the stronger the interaction is. Okay, so that's what we're looking at here. This is the effect on this diagram right here. Now then, what's the point? And if you think just for a second, what we've done is we've just plotted these 4 points. So there's 4 points. Those 4 results got plotted to make this diagram. So what's the beauty of an interaction? Well, it's like this, of course. This line, let's label it, is the B plus 1 line. So when B was all the way to the positive, A drives the result higher. But if B gets switched all the way to the negative, A will start to drive the result down. It'll drive it lower. But here's the point. There is a point here, of course, because we don't have to go from all the way from B to the positive to all the way to the negative. We could pick some value of B in between. So what we could pick is B to the 0. And when B goes to the 0, what happens? The result goes horizontal. Now, when the result is horizontal, by the way, just to point out, it doesn't have to be the mid value. It has to be a value. Obviously, the result is swinging all the way from the positive to the negative. There is a point in those settings where the line goes horizontal. That's the setting we're looking for. In this case, B to the midpoint is probably going to be it. And when B is at the midpoint, A has no effect. A is having no effect. A has no effect. What does that mean? Well, it means we've switched A off. So if A was something that we were finding it difficult to control, let's say we were trying to control the water temperature of a bath in a plating plant where cold water is constantly flowing into the bath. There's a heater at the bottom of the bath and we're trying to keep the temperature at a particular value and we are struggling to do that. Maybe we want to turn the effect of this thing off, because if A is having an effect and it's doing something, it's going to do this to the process. Whereas what we've done, by turning the sensitivity of A to the lowest possible level, making the effect horizontal, we've switched A off. That is a robust setting. The process now is robust to the variability and the movement of A. Now that is robustness the mathematician's way. We've already looked at robustness Taguchi's way. Now what we're going to do, because this is a little bit more technical than Taguchi's technique, in the next video we are going to take a look at 2 exercises. The first exercise, I'm going to show you how to do this in a real situation. The second exercise, of course, I want you to shut the video down halfway through and for you to do the analysis yourself and be comfortable that you've found a robust setting. So this is robustness the mathematician's way. I will see you for the exercise in the next video.